Okay, so thank you very much for giving me this opportunity. It's a wonderful program. So C, sensor number 1 is a symmetric monoidal category. So if we have such a category, we can form the Picard group of C, which is isomorphism classes of invertible objects in C. And for this to be a set, we should probably assume that our categories may be presentable, or locally presentable or something like that. Otherwise, might be a proper class. So that's a space. We've had a lot of pick activity this we had confusing picks, I think was.
No, that wasn't me.
Huh?
That wasn't me.
That was not you.
Werner.
Hans Werner had confusing picks, but you had some other.
Vesna
Vesna had dreaming picks. You also had some picks, right? Huh?
I had unit.
Oh, you okay.
You're getting really picky.
Okay, so we have that. We can also, if we instead of saying, of course we don't just want this group, we want maybe a stable infinity category, because then the great thing about that is that we can form the space of these things. So this is the space, or the infinity group point if you want, of invertible objects and equivalences between them. So that's the space. And we can, in general, so that's a space, it's even a group like topological monoid, it's an infinity space. So so it even has a de-looping. And in general, we can describe what the Picard group, the homotopy group, so such a thing is. C, as our pi naught.
What was the word after invertible in that definition? Space of invertible something.
Objects.
And how is this a space?
So if you have two objects, you have all the equivalences between those two objects. That's an infinity group point. So that's a space of things.
All right.
They can also. Okay, so we have pick C if I is equal to 0. If I is equal to 1, we have the units in the endomorphisms, the endomorphism space in C of the unit. I is equal to 1, and if I, we just have pi I minus 1, up again the endomorphism space of the unit here. So that's a nice space we can understand. Hopefully, if we know the category, then you know the Picard group is just as mysterious as it was before. If we know our category, we might know what the endomorphisms are. We know what pi naught, and we know what the units are. We might know also what the higher homotopy groups are. So that's the general setup. We've heard many talks with similar setups and similar categories. So in this talk, we'll have C is just a stable module category of Kg, where G is a finite group. K is a fluid characteristic P. That's a fine. So the fine is that we have, as usual, we have the module category of Kg, where our objects are G modules, and our morphisms But we could also say that two of these things were equivalent if they factor through a projective. So we have a notion of equivalence. Where we say that two morphisms G and to N are equivalent if they factor through a projection. So that gives us
difference.
Huh?
The difference.
The different factors through. So that gives us a notion of homotopy equivalence. It gives us a notion of when homotopy, so it gives us a notion of homotopy equivalent, namely if you can find maps back and forth so that they compose to the identity up to homotopy. This is a fine category. It's a model category with the objects with the co-fibrations, being the injections, and the fibrations being surjections. So it's a little bit of a funny model category in the sense that all objects are fibrant and co-fibrant, but that's sort of just the way it goes.
Modules are not finitely generated.
Modules do not have to be finitely generated. For the purpose of calculating the Picard group, it reduces to a question of understanding the compact object, so therefore you might want to understand the full category, but for this purpose you might just want to understand sort of the little thing here. So then we can also form the infinity category. So these are some equivalences. This gives the notion of equivalence, which we call W. So we can form if we have this category of modules, Kg, and invert the weak equivalences, then we get a fine infinity category that we can study. We can also view, so Lars asked about compact objects. In this case, one can see that these arbitrary objects are the sort of what you get from the compact objects by freely allowing colimits, since it goes on the level of just objects, that everything can be obtained as a filtered colimit of the finite ones. So this, I guess we could say that this is an incompletion of the compact objects mod of Kg, and at least for the state mod of Kg, it has a sort of another nice description which is good to keep in mind. Namely, so one of the slightly annoying things about the stable module category was that it was in a way a little bit too nice, that we didn't have sort of this simplicial structure. Everything was concentrated in degree 0, and that might sort of confuse you into thinking that the harms, sort of the derived harms in this category, should just be, the actual harms between the two objects, which is not correct, despite all objects being co-fibers. So it gives you the right pi naught, but it's not the right mapping space. A good way to view this is that if you look at the finite ones, then you can view that as a quotient, one of these Verdier quotients, where you take the bounded derived category and mod out by the perfect objects. So that gives us another good way of at least understanding the compact objects. And it's a corresponding statement on the full thing, which one might want to study. So here we see, we can easily see what sort of the mapping spaces are, because they are actually, you take them in chain complexes, where you take resolutions and then what. So in particular, if we go and say what is our Picard space in this case, then we just get pi I of Pic of the mod. What is that? It is, well, it is what it is in degree 0. So since it's only being invertible only does not involve any spaces, then this is something only determined by the homotopy category. So this would be the same as what we had in the homotopy category, or the stable model category. If we take pi 1, then we have to take the endomorphism, so that's sort of like an X thing from K to K, and then we take the invertible things, so we get K star, and for the higher ones we get the group cohomology of G. Okay, sorry about that.
Is that with trivial X?
With the trivial action, yeah. It's just the X algebra.
So this is a table I equals 0, 1, and
This is I equal to 0, this is I equal to 1, this is I greater than 1. So we at least, we understand the Picard space, except we don't understand pi naught, which is of course maybe what we really wanted to understand in the first place. But so this is a classical. So now I sort of thought it was fun to inspired by Stefan to give this introduction where I presented this in using saying the general framework here, but this is really a classical story of understanding these groups. So there's a classical story which so these objects here are called, so this thing here is called the group of endotrivial modules. So this is something which people have been studied since forever. So in group theoretic language, this is isomorphism of classes and modules M, so that M is homotopy equivalent to the trivial module plus a projective module.
Then you can write isomorphic. It's correct, but if you say plus projective, you can write
Isomorphic. Good. And Lars asked again about finite. So when M is finitely generated, then this is the same as the endomorphisms of M. And in general, all of these modules will automatically be finitely generated. This satisfies this property. So this is a general categorical thing. You can also see it here via sort of a small calculation. So this is why the name endotrivial comes. The endomorphisms are sort of trivial up to projective. Good. So as I mentioned, at some point this will be joint work with these people here, which are algebraics, and with Tobias Barthel, who's sitting there, and Joshua Hunt, who was here earlier, and who is my student. This last part of it is part of his master's thesis, so he's still around and doing excellent. Good. So the first term to know is Baden. Two celebrated papers in Jounce from 78 prove that if B is an abelian finite P group, then this group here is in fact very simple. It's just generated by a Hiller shift of the trigger module. So this is the loops in the stable module category, so we take a projective mapping into it and take the kernel. That's the loop over a DC spectrum. So this is a generator, and what is this? Well, so then we have to look at resolutions. If the group has order 2, it's 0 because the resolution just, you map the group in, and then the kernel would be the trivial module again. If Z modulo 2, if G is cyclic, and the order is greater than 2, and otherwise this resolution does not repeat itself. Then there's a theorem of proof, maybe also around 1980, which says that this group is finitely generated. So there should be a group that you can actually calculate which is finitely generated, or at least hope to calculate. And then there's a theorem of Alfred, I think was around 1990, maybe a little bit before, which gave a formula for the torsion free rank. Rank of G, K, G, again, if G is a P group. When I say P group, I mean a finite P group. Basically describing the rank in terms of the number of these rank 2, maximum rank 2 elementary abelian subgroups, so it's sort of a restriction to Date's result. And then Carlson and Temenas also in 2 long celebrated papers in 2005-6 actually gave a description of the torsion part of this group when G is a P group. So if G is a P group, find a P group again, then GK G torsion is equal to 0 unless G is cyclic. We already saw that sometimes in the cyclic case you got C mod 2 semi-dihedral, in which case you get a Z modulo 2 or generalized quaternion. In which case you get Z modulo 4 times Z modulo 2. So this happens if the Z modulo 2 is only there if K has third realization. So it's really, I wanted to put it up here because this shows that, it's really a sort of fairly manageable list. So this gives you a complete description of what this group is for any finite P group.
Do these people specify generators for these groups?
Yeah. And it's not so. The sort of the Z modulo 4 is because the quaternion group acts on the 3 sphere. The 2 other ones are slightly less obvious. So, of course, now we know what is our solemn duty to attempt. So this is for P groups, right? So then you might ask, what happens for finite groups, for arbitrary finite groups? And this is actually people thought.
Is it also known how to find generators for the torsion?
It is known how to find generator for the torsion free part in the P group case. Yes. So now these arbitrary finite, in essence, a single P group. Well, then there's an obvious thing to try, or to say. Now we want to understand the Picard group of KG, and we know how it we know what happens. We completely know this group here, so we can look at the restriction map. And we can look at the kernel. And then question 1 is what is TKD, and what is it? It's the image of the restriction. So these are the two questions you might ask. So people started, since this is such like a small group, you can sort of basically try to sort of case by case to try to find, and there's so little torsion, you can try to see if you can find out at least what the image here is as an abstract group. So this is like Carlson, Mazza, seminars. They determined, so this has some image, let's call that L, which is inside here. They determined L as an abstract group. So they found out what the torsion group was and what the torsion-free rank was, but not the generators. So, but they also said that this was split in all cases except the place where it's cyclic, where we also completely know what's going on. So we're just interested in knowing this as an abstract group, which is we're of course not satisfied with, but if we were satisfied with knowing that, then the problem would boil down to completely understanding this group. So that would really be good. So I'll talk about the two parts. I'll talk about what this group is, which is the work where I did sort of the first part, and then I also collaborated with these algebras to try to do it for some specific groups, and then I'll talk about what this image here, which is the part that should be as
So if we want a natural description of this, one question that you can remind me of is what the functoriality in G is. So for which homomorphisms in G go projectives to projectives, and hence we get an induced map.
So if you restrict, then you
Yeah, but you can try more general things than restrict into subgroups. You can inflate or something like
right,
this.
yeah.
When
So
does
it
this work?
depends if you have if you have modded out by a P prime group, then you still be projected. If you modded out by something which was like
So the kernel shouldn't be
prime
defined by
to
P.
P,
Okay.
Since you have a space, I thought you were going to ask when do you get a vibration in infinity categories?
When you get a vibration of infinity categories
Of complexity.
between these,
Yeah, still talking about the functoriality in G.
right? Just on that. Yeah, I don't think.
Vibration, of course, but it becomes less calculation.
So the Picard space functor commutes with colimits. So if you have the limits commutes with limits. With both.
Filtered.
It also
Filtered colimits.
filtered colimits. It commutes with filtered colimits or infinity. I'm so glad I can be obvious. And arbitrary limits of infinity categories.
Of symmetric monoidal infinity categories.
Symmetric monoidal infinity category. Otherwise, it would not make any sense. Symmetric monoidal.
Well, the functors better be strong monoidal, otherwise I think it's also not.
So, yeah, and then of course, so that would convert a limit of infinity categories to a limit of spaces, which is like a limit, like a homotopy limit of spaces, which is something we know classically and we have obstruction theory. And that'll be a point in the last part of the talk. Good. Other questions? No. this was a good audience to give this talk to. So this was like a theorem of mine from Nakano a couple of years ago. So this gives a description of this kernel here, which is that this is isomorphic to the H1 over the p orbit category with coefficients in k star. So this is the orbit category, the p orbit category. So this is the orbit category with object t mod p, where p is a p subgroup, and the star means that I exclude the trivial subgroup. Because somehow if I had the trivial subgroup in there, I would sort of have G in there, and then would sort of force, all these things to be one dimensional.
Right on the board, what's the definition?
Yes,
So this is G mod P, where P is a non-trivial P subgroup. So it's the orbit category, right? So with objects T mod P, where P is a non-trivial P subgroup of G.
What
More
does
than
P
G
subgroup?
T mod P, that's a G set.
No, what does P subgroup mean?
It's a subgroup of order. The order of the group is a power of P.
Yeah,
Right. So this gives a description of this group as sort of an obvious candidate. Like, so groups which are obviously in here would be the one-dimensional characters of G. They restrict trivial to the zero subgroup. You have a one-dimensional. If you have a one-dimensional representation of G, then it restricts trivially to the zero subgroup. But people have observed that there were others of these, and this gives a complete description of what they are. They are sort of they are the one-dimensional characters in a way, but not the one-dimensional characters of the group, but rather the one-dimensional character of this category. So this is of course the same. This is with trivial coefficients. This is simply the Hom from pi 1 of the p orbit category of G to k star. And I show that this group here is a finite p group, finite p prime group. So this is a finite p prime group that you can calculate. I give a description of this group in terms of generators and relations. It's always a quotient of the normalizer of the CELO, modulo of the CELO. So it's in general, it's a fairly small p prime group. So let me, here, so we have a surjection from the normalizer of the CELO, modulo of the CELO, to this group. So it's really a small p prime group in general. Sometimes, if the CELO is self-normalizes, it's a trivial. But in general, it's a group, and it surjects onto the obvious candidate for what it also could be, namely G modulo the subgroup generated by elements of p power order. So this is sort of the smallest p prime quotient of G. So it's a group which sits in between these two groups. It's a small group of p prime order. Now, and so I'll give a bunch of theorems which actually, states all sorts of ways that you can calculate this group. This is the kind of things that, that we spend a lot of time calculating fundamental groups of various categories, and Bob and Carlson and all there. So, look in also these for fusion systems and things like that. So there's really a lot of tools for calculating such a group here. Let me also say what the equivalence is between these, what the isomorphism is. So the isomorphism, the one way, takes a module, and then assigns to that a functor on the orbit category, which to a G set G mod P, associates the zero state cohomology of P with coefficients in M. So this is just the fixed points modulo the image of the transfer. So it's such a a one-dimensional module because by the property of line is correct. So I should also say that by definition, this group is just the modules such that if you take this module and restrict it to the zero subgroup, then this is isomorphic to K cross projective. So we sort of, this end of things goes away. Simply the modules, which once we restrict to zero, splits as K cross projective. So it's a very natural class of modules. So now you might say, so this is a function of the orbit category to one-dimensional modules and isomorphisms. But the category of one-dimensional modules and isomorphisms is the same, is equivalent to K star. So this is the same. We have one of these. This is like this coefficient system where you have a sequence of one-dimensional modules, and to that, that's the same thing. It's the same as saying a function. So K star. So this is how we get the element H1. And then we also show how to go the other way, because part of the what one might like about this is that you get to say infinity category and write up a very specific modules in the same talk. That's an appeal. So the function going the other way says, well, given we have phi, one of these orientations you can think of them, or one-dimensional characters of this group, we associate it to K phi, which is again this local coefficient system, one-dimensional modules. And what do we assign to this? Well, we look at the subgroup complex of G. So this is a P subgroup complex. Of P subgroup, chains of P subgroups. And then we give it this local coefficient system via this here. So then, and once you see that this is a formula, it's sort of not, there's a classical theorem of equivalent, which says that if this twisting is trivial, then this complex here is equivalent to the trivial one. So,
but now I should interpret this in dB mod perf.
So this is now exactly, this is an element now in D, E, K, T mod perf of KT. So this is, but by what I said originally, this is an element in the mod. But you can really, in practice, often, there are not so many cases where this is trivial. So actually whether you have these non-trivial twistings, in many cases, like this complex will actually be one-dimensional or something like that. So then you can sort of really explicitly, you really get a module out here as a kernel of that. So, it's a formula. You can write down what the module, you can say what the dimension is, and all these things which people sometimes like to do. But also now, now we, right, this is what I have to say about the proof. So the proof is basically that you can follow Quillen's argument by with more modifications, and then you get this. But the way to interpret, and the way I sort of first thought of it, is that it's a left Kahn extension. You have a bunch of one-dimensional modules lying on this orbit category, except the trivial subgroup, and then you look at the inclusion into the whole thing, and then you can Kahn extend along, or homotopy Kahn extend along this. You work out what the formula for this is, it's exactly this. So now you have a function in the orbit category, but in particular you have it on the trivial subgroup. So that gives you a G module. So it's sort of like, it is sort of an induction procedure, but now sort of induction a little bit more complicated than group theories usually do, where they induct from the subgroup. Right? But here we induct from like a family of subgroups that we take at the same time. So then, let me just sort of state some of these formulas that you can get. So you get now. So now, this orbit category, there's all these homology decomposition techniques. So what you get is that you for instance get a. Also, so let me just introduce one subgroup. I apologize for the piece of group theory, but it's like a subgroup which plays a big role in all of this. Is a subgroup generated by normalizers of all p subgroups which lie inside the zero and are non-trivial. In many cases, this subgroup here, if it's a proper subgroup, this is called the group having a strongly p-embedded subgroup. And there's a classification actually for when this happens. The group theorists have found out exactly when this is a proper subgroup of P. So this is for the prime 2, this is a theorem of Bender, which is used in the classification of finite simple groups. And for odd primes, it's a consequence of the classification for finite simple groups. But it's something which they use sort of all over the case. So the first theorem here is that a first approximation to what these one-dimensional characters would be the one-dimensional character on this subgroup here. Then the sequence goes to TKT, S, and goes to H1 of the P subgroup complex, again on this G naught. And then you have to take G invariance here for the subgroup, and then it goes to H2 of G naught with ordinary group homology with characteristics in K star. So you have such a sequence here. So in particular, if the subgroup complex is simply connected, then this group is simply with a K star. Here I could either do with SPG or SPG naught. So SPG naught would be the connected component of the space. So that's the geometric interpretation. It's simply connected. So the geometric interpretation is that this space is connected if and only if G is equal to G naught. Then there's like TK S. You can again. So this follows just by looking at you have a group action. G acts on this building, so on the subgroup complex, and you look at the Serre spectral sequence for that thing, and that gives you a formula for what this OP star G is. So then you get this formula. So this is just sort of once you have the first formula, it's using the Serre spectral sequence. You can also use an isotropy spectral sequence. Then you get a formula in terms of a lim 0 over all the P subgroups of simply the maps from such things to K star. So this gives a sort of an algorithmic way of calculating this group is, right? You have to calculate all these homomorphisms. These are standard homomorphisms, and you have to see how they fit together. So this is something. So this was a conjecture of Carlson and Sevenats, which, I mean, they didn't formulate it as a lim 0, but they had sort of an algorithm for calculating. They had a guess for an algorithm for calculating this group, and they conjectured that this algorithm always computed the right thing, and this affirms that.
If you take the mapping fiber of the induced map of Picard spaces, do you then get the integral 0?
If you take the induced map on.
So this thing here,
right,
isn't that pi 0 of this?
Yes. So say that question.
But there could be pi 1 of the Picard space of S
Okay.
coming from behind.
Right, yeah. And it's something like that, where you can, this is one way to we'll see that when we deal with the co-kernel, is the story there, how this group comes up.
Yes, can one interpret this one to say that TKG S is the same as TKG0?
Sorry? Say.
Do you know the relation between TKGS and TKG0S?
Well, they're the same, yeah, sorry,
Always.
they're always the same, yeah. And that's also easy to see from this picture, and it's something which also can be useful for homotopy series problems. The orbit category here are simply equivalent. Actually, when preparing this talk, I looked at a paper by Keel yesterday where if you use this observation, like a lot of the relations would have been obvious. But this is like, I'm just saying that sometimes there's this finite group theory, which is actually, every time the orbit category comes up, if you're doing something with p subgroups, then, then this is a good group to keep in mind. Oh, and I might want, so the last thing, which is also useful, is that so there's some people interested in fusion systems, so you can look at the H1 of the fusion system. So this is where you, instead of taking maps of orbits, then you take homomorphisms of p groups as your maps in the category. So the automorphisms will now, instead of being the normalizer mod p, will be the normalizer modulo the centralizer of p. And this is something which is only depending on the fusion system or the p-local structure. And this is a sequence like this, TKD by S going to 0 over decentralizers, the G, car. And this is over the fusion category going to H2 of this P star. This is also sort of interesting in the sense that this shows that there's a part of this Picard group which only depends on the fusion system. So anytime you have a group in that fusion system, which is sort of less information than the orbit category, then you have these chunks sitting inside it. So before talking about more abstract stuff, let me just mention that, or talking about this step 2, let me say that this actually now enables you to calculate what this group is for a lot of finite groups that we might care about. So remark, for instance, that SPG is known to be simply connected for symmetric groups, finite groups of D type at characteristic P. So if you're at characteristic P, this is just a Chitz building. So that's known to be, a Warshaw sphere. So it's, in particular, the fundamental group is 0 once you get a little bit often. Yes, this has exceptions if the group is a symmetric group and the finite group D type are like rank 1 or 2 or something like that. And so I also tried this formula out on the sporadic group. So you can, for instance, see that these groups here vanish for the monster, for instance. So this T comma S is 0 for P equals to 2, 3, 5, 7, 11, and 13 for B is the monster. This was known before for the prime 2, just because it's self-normalizing the subgroup, but it was new for these other primes. So yeah, people have looked at this sort of with character methods and things like that. But I mean, I think this gets also the computations a little bit further.
So you really made it. You have one paper with stable infinity categories and one with a monster.
Yeah.
This is their one.
So you can, for instance, I mean, let me just, obviously, let me just say the upshot of this project with Carlson. Mazza and Nakano. Well, then says that if G is a finite group of these type, and N is the characteristic, K is now different from the characteristic P of the group, different from the defining characteristic, then also this TK GS consists of one-dimensional characters, except if L is equal to 3, and we're dealing with B2, 2, G2, 2, A3, 2, or L is equal to 5, and we're dealing with B4, 2, F4, 2, E7, 2, or E7, 3, and then here you have to take the universal form, so it comes in two forms. So these are the exceptions. So and it turns out, if you study these finite groups of Lie type, then what happens is that sometimes H1 of those finite groups of Lie type is not what you would expect. Sometimes it happens that they have, a perfect subgroup. They have they're not perfect groups, even though they should be, and that was classified by Teets exactly when this happened, and it happens for a bunch of these like small groups. For instance, like the Teets group, which is the twisted form of F42, is one of those examples. And then if you have one of these examples on H1, then that can sort of rise because you're taking a co-limit. And then if one of the H1s are sort of wrong, then that can propagate to give a new one-dimensional character, this OP star G. So this is what happens. It gives rise to these examples. But you can see that, that bad behavior quits after a while, and you only get these examples. And it's always sort of this gives a set modulo 2. If there's 2 here, it's a set modulo 2 you get here, and here you get a set modulo 3. So they're very limited. But, okay, so that's computations. Let's move on to my question 2. So 2 was, so now we know that we have this sequence from this OP star T goes to TK G, and then I said, well, you map to TK S, but you could do this, for all the different subgroups. So you could map here into the inverse limit here over OPG star, and then you could plug in P here and take the inverse limit over. No, sorry, this is what I don't want to say. You could have a map to here. Now finding explicit generators for the image here, if you really want to understand what the group is, not just as an abstract group, you want to find what the generators are. And that would amount to finding, exactly what the image of this restriction map is. And you can in particular ask if this, if this map is untrue. So this is this thing which is done here with the
So I'm slightly confused. The Silo subgroup is one of these P's, right?
The Silo subgroup is one of those things.
Why is it better to add more?
Well, so
They're all going to factor through the Silo subgroup.
all going to factor, but there's some relations. So now you're saying that you have a map into the Silo subgroup. It's sort of like the stable elements formula
Yeah.
group Copenhagen. So it puts relations between the different subgroups. So yeah, they need to be the same when restricted to groups which are conjugated in the P group. So here's our. Hunt, which says that this we have a sequence like this, but it's not quite exact. We have a differential which goes here to H2 over the whole category with values in K star. So then you might ask, what is this map exactly? Well, so first of all, you could ask, is this map then, is this map trivial or not? So let me also say, one version of what I prove with this Carlson conjecture says that this could be reformulated as having the chronology of this one-dimensional characters on this P subgroup complex. This is what rewrite this inversion. Then one of the things we show is that this map here factors not necessarily to the whole thing, but it goes via H1 relative variance S1 of this with values. Okay, sorry. So we have a factorization like that, and the map G is 0 when P is equal to 2. So if we're in the characteristic 2 situation, then this is actually an exact sequence, and we get a complete description of the generators. But for P odd, for P odd, we have a combinatorial or group theoretic description of a P, but need not be 0. So this map need not be 0. But we can sort of say explicitly what it is in terms of resolutions, and so the easiest thing is to see if it's 0 in here, which build out which comes down to various congruence conditions. So let me say so I'll not spill out the congruent conditions, but so in particular, so here's an addendum. D is non-trivial for P equals to P SL to FP, and P is congruent to 1 mod 3, so it has an image is of order 3. So this has order 3 for this.
For what, yeah?
For sorry, for at the characteristic. So L is equal to 2. Yeah. Thanks. For this P here. The image has order 3. So in particular, P does not fusion does not determine image. So this image here is something which is only depending on fusion in the group, and there was a conjecture by again Carlson, and Mazza that if you had a fusion preserving map between the fusion, which was map between groups, which was an isomorphism of the fusion systems, then they had the same torsion-free part here, and this is not true. And also the modules need not lie in the principal block. So all these two statements here are counterexamples to conjectures of Carlson and Mazza and so some of them have positive answers, some of them have negative answers.
Did you say principal block?
Need not line the principal block, yeah. So if you're familiar with blocks here, this is a block of the splits up. The module category splits up to this block, and the principal block is the one trivial module. So that turns out not to be true. So I have 3 minutes to discuss proofs of the last part. So let me say maybe split it, so I say a couple of. So first, like you can say, okay, given you have the result, how do you get the counterexample? And the counterexample comes exactly by the interplay of these p elements part of the p prime parts. So you can sort of, we know once we restrict to elementary abelian subgroups, it just becomes a Hiller shift of the trivial module. But there's sort of like an action, there's a p prime action on it. So like, say if you have something like C mod 7, C3 or something like that, look at the resolution of that, it's 6-fold periodic. So if you now look at the group like this, we could restrict both to this subgroup, to this subgroup, to this subgroup. And there's limits to what one-dimensional characters the normalizers of these groups can have. And that translates into, once you go through the resolutions, that translates into a congruency condition in terms of what the dimension of the shift of the module can be once you restrict to these different subgroups. So that gives us sort of a congruent condition, and it's a subgroup that satisfies those congruence conditions. So that's sort of the very, very short idea of how you get some things like this. But in general, it's not subjective. Let me also say something about one way to derive this map in the last 2 minutes, because then I'll return to the infinity categories. So one. So the stable module category you can write as a homotopy limit of the stable module category of KP over the P order category. This follows by, I think, Matthew, probably well known to those who know it well. So then, then we're interested in the mod of KG, but now we've expressed it as a homotopy limit, and now we know that the Picard space commutes with the limit, so now we get a whole limit over the mod here of KP's over again OP over category. Huh? I forgot the pick.
There's also a big mod on top there.
This fits. So, but now this is a homotopy limit of spaces, right? So now we have a spectral sequence. So ij of pick of this the mod for KP converting to I j of KG. So we have our spectral sequence. So this is one of these fringed babies, so have to be a little bit careful if I do the CR grading, which everyone is going to hate me for. Then we're trying to find an element here. Then we have, elements here. This is a 0 line. This is a minus. This is a -1 line. This is a 0 line. And so here you have H1, P star, K star. We have a here we have a H2 OP star. So in order to see the lifting, we need to see that this differential, it's whether or not this differential vanishes or maybe the higher. Luckily, all this stuff here up is 0, so we have an existence obstruction which lies in here, and a uniqueness obstruction which lies in there, which gives us a sequence of this point. So yeah, but so this is, and then you can sort of get this better thing by again looking at some other spectral sequences to actually see that it lies in this subthing. So that's how that goes. Good. Thank you.
Our questions.
Is there anything understood about the analogous things when you replace the field K by like a larger ring, like the integers or
Yeah. So all of this, I mean, all of this lifts to at least to did over like a corresponding discrete valuation ring. If you had arbitrary rings, I mean, I don't. Yeah. So then you get into maybe then we have to talk about relative projective, and I mean there's some issues there. I mean there are people who've studied also the thing. You just need to get one of the things you need to get off the ground by studying this like singularity category for these rings, and I think Greg Stevenson has the analogous of this. I mean the first just even studying the stable module category in that setting the first time. Yes, that's. I mean. I think every time you get like a situation where you have the orbit category, it makes sense to remember that category has some topology. And one of the things, which when I've been doing a lot of things which are sort of at the prime P, where things are always P local. But the thing is, once you study these Picard spaces, right, then it has some P prime information sitting there at the very bottom as a pi 1. And that that also occurs in all sorts of other categories, and that's should give rise to similar things on the orbit category.
More questions?
Is there a Bravo group?
Yeah, that's a good question. We've asked ourselves that question as well. Yeah, so it was natural to think that sort of that this H2 had a relationship to some Bravo group. So we haven't sort of quite been able to get something really, use that perspective to anything. But in this case, like the H2, actually, often this identifies with the group cohomology. So somehow, maybe a way of thinking of it, like naively at least, is just simply the same thing as H2 of a finite group, right? So it's a question of like lifting projective representations to actual representation. For instance, in this counter example, this H2 is equal to Z modulo 2 when the generator is the fact that that has a universal cover. So that's sort of more elementary maybe, but there could be a more fancy interpretation.
Anything else? Let's thank Jesper again.